Determine the internal shear and moment in the beam as a function of x. To solve this problem, we have to cut our beam at x. Let's draw its free body diagram. We're going to have a beam something like this, and then a cut. At the cut, we're going to have our shear, our normal, which is 0, and a moment. And we have our unknown distributed load, which we're going to find out really soon, and our point load of 6 kilonewton. Now, to determine our uniform distributed load, we need to use proportionality. So we know that the full uniform load on this beam is 18 over 3 meters. Similarly, we're going to name this as a U, and this U runs along till x. Solving for U, we get our solution as 6 over x. Pardon me, 6 times x. Once we have this, we can basically sum the forces in y direction to find our equation for the shear. So we can have negative V, negative 6 kilonewton, and then our point load from the uniform distributed load, which is basically half times 6x times x. Solving this becomes 3x squared. So all we have to do is add that into our equilibrium equation here. So it's going to be negative 3x squared, all equals to 0. Solving for shear, we get a solution as negative 6 kilonewton, negative 3 squared. All of this is in kilonewton. Similarly, to find our moment at x, we're going to have to sum the forces at our cut. So by using the moment equation, we're going to have our unknown moment, positive, and we can have positive 3 squared, and it's x divided by 3 meters away. And then we have our counterclockwise external load of 6 kilonewton, and it's x meters away, all equals to 0. Solving for m, we're going to have x cubed negative and negative 6x. All of this. For this problem, determine the internal shear and moment in the beam as a function of x. Just like before, you're going to have to, first of all, determine our external load for this beam. So we know that at pin connection A, we're going to have AX, which is going to be 0. Because by inspection, we can see there isn't any horizontal force acting on it. AY, which we have to find, so is BY. But because we are just looking for a function of x, we just have to find the left-hand side or our vertical direction at point A. And that will be all to solve this problem. But before we start solving for external reaction force, first of all, we need to convert our uniform load into a point load. So we're going to have to use the area of triangle for this uniform load. So it's going to be half times 12 times 6. And solving that, we get our solution at 36 kilonewton, and it's 2 meters away from B. Now we can use equilibrium equation, the moment equilibrium equation, to determine our solution for AY. We're going to sum the forces along B. We're going to have 36 kilonewton counterclockwise, and it's 2 meters away. Then we have clockwise AY, and it's 6 meters away, all equals to 0. Solving for AY, we get our solution as 12 kilonewton. Now we can start proceeding by cutting our beam at X, which is imaginary, which could be at anywhere. So let's draw its free body diagram. So our beam is going to look something like this, where we have AY on one side, and it's 12 kilonewton. Then we have our triangular uniform distributed load, and we still need to find our value for this new uniform load after the cut. And at cut, we're going to have our shear, our normal, which is going to be 0, and our moment. Okay. As just like before, we're going to use proportionality to determine the extent of this triangular uniform load. So we're going to have, we know that the original uniform load is 12 kilonewton per meter, and it's along 6 meters. Our new uniform distributed load is U. We're going to name it U, and it runs along X meters. Solving for U, we get our solution as 2X. And this is kilonewtons times per meter. Okay, so now we can simply sum the forces in y direction to find our solution for our shear. We're going to have 12 kilonewton, and then we can just quickly find our point load for the distributed load. So it's going to be half times 2x times x, so basically x squared. We have negative x squared and negative shear, all equals to 0. Solving for shear, we get our solution as x squared negative 12. Well, we can't really miss our negative from the shear, so dividing both sides, or you can say multiply both sides by the negative, we're going to get our solution as positive 12 and negative x squared. Both of these are the solution is in kilonewtons. Now we can take a moment about the cut. We're going to have x squared, and it's x divided by 3 meters away. And then we have our AY clockwise, and it's x meters away. And finally, we have our positive moment at the cut, all equals to 0. Solving for moment, we get our solution as x cubed divided by 3, take away, negative x cubed divided by 3, and positive 12x as our solution. And determine the internal shear and moment in the beam as a function of x throughout the beam. Looking at this beam, we need to realize that we need to solve for this beam in 2 stages. One would be between 0 and 2, and second would be from 2 till 4. To begin with our first section, let's draw its free body diagram. We're going to have our beam, and one end we're going to have a cut, where we're going to have our shear, our normal force. A normal force will be 0 in this case because there isn't any external horizontal force acting on this beam. And on the opposite end, we have 20 kilonewton times meters moment in counterclockwise direction. And for this section, our shear is also going to be 0 because we don't have any vertical force acting on this beam, or at least this section. And then for our moment, because it's a super simple version, we can solve without even using our moment equilibrium equation. And we know that our moment for this cut is going to be negative 20 kilonewton times meter. Now we can draw our free body diagram for second half or second phase of this beam. So we're going to have beam with a cut after 2 meters somewhere, and then we're going to have our shear. Our normal is going to be 0 for this cut as well, And our unknown moment, we have our uniform distributed load, which is 5 times x take away 2, or simplified 5x take away 10. And then right after this uniform load, we have our counterclockwise moment of 15 kilonewton times meter, and then our final moment at A of 20 kilonewton times meter. Now to solve for this problem, we can use vertical equilibrium equation by summing the forces in y direction. We're going to have our uniform distributed load, which I've already converted into point load, but I did not mention it. I just did it in my head and didn't realize I didn't put our distinctive vector for the point load. But anyways, moving on. So we're going to have 5x negative 10, and then our unknown shear, all equals to 0. Solving for shear, we can have a solution as negative 5x plus 10. This whole section will be kilonewton. Okay, now we can sum the forces, or rather take a moment about the cut. So we're going to have our unknown moment, and then we have our point load from the uniform load, and it's counterclockwise, so it's 5x negative 10 times x take away 2 divided by 2, which in other words is simply x divided by 2 take away 1, and then our counterclockwise moments 15 and 20, all equal to 0. Simplifying this, we get something like this, all equals to 0, and then solving for moment, we get our solution as negative 5x squared divided by 2 plus 10x take away 45. All of this is in